starting a new unit today. Okay? It's on something very near and dear and familiar to you. It's on gases. This is a chapter that we do. It's a unit that we do. This is not something just for filming. Yeah, the camera is on, but guys, I will be picking 20 minutes total out of 4 classes. Don't worry about it. Okay? What they're looking for again is discussion about science. And basically that means demonstrations and your responses to them about science. This is a unit we would learn. 6 periods going to come in here, and I'm not videotaping in here. And they're going to get exactly the same unit that you're getting. You're not getting this just for the tape. I decided to do the tape today because this is a unit that I felt would tape well. But it's not a special unit that was designed just for tape. You'd be getting this regardless. Try not to be too self-conscious about it. I know that that is hard. I know that it's hard not to be self-conscious with a camera in front of you. Remember that the only person that's going to watch this silly thing is some teacher in a room somewhere looking at it and reading a commentary on it. It's not for broadcast. Okay? So relax a little bit. The unit that we're starting is gases, behavior of gases, something called gas laws. Is there gas in this room?
Yes.
There's gas in this room. I'm going to take some and put it in here. You started probably doing this when you were maybe 4 or 5 years old, filling up balloons. Specifically, what's in the balloon? Your gas,
Carbon dioxide.
I hear carbon dioxide, nitrogen, water vapor, oxygen. It's a soup we call air. Okay, lots of different gases that are in here. I'm using the balloon to make the air visible to us. The balloon is not important in itself as it is as a vessel for us to be able to see the balloon, the gas that's in here. We normally couldn't see air, just in the room. If I wanted to make a balloon bigger than this one, I could do so by changing what? By adding more, blowing longer, putting more particles in, and I would make a bigger balloon. But we also know that balloons are mostly empty space, and the size of the balloon actually depends on more than just the amount of air, more than just the number of particles that are put in it.
The amount of expansion of the balloon?
The amount of expansion, or the other way of thinking, it would be the amount of compression. During the chapter on kinetic energy, kinetic theory, you saw me compress gas, so you know it's mostly empty space. And what we're going to be looking at are ways that affect what we see as the attributes, the size of the balloon, the volume, the temperature, the pressure. And the first relationship we're going to look at is called Boyle's law. It's a pressure-volume relationship that reads, volume varies inversely with pressure. Underneath those words, you see kind of a funny mathematical statement that says P, and it's got sort of like a fish-shaped thing, 1 over V. Does anybody recognize that symbol from math? Look familiar? You'll get to it
The
eventually.
angle?
Not an angle. It's called a proportion sign.
Oh, yeah.
Oh, yeah? Okay, which math did they?
I think that was like the last part of the year of algebra 2.
Okay, it hasn't really been emphasized yet, but it will. Okay, proportions are important. We can't just plug them in as numbers, but they're really good at looking at relationships. It's a way of, in shorthand, writing that volume varies inversely with pressure, meaning as one gets bigger, the other one gets smaller. And that's what we want to demonstrate first. I'm going to take our balloon and I'm going to put it into a system at a pressure that, let's take a guess at. If I talk about pressure in this dome, what would it be right now? Close to 101.3 kilopascals. Have I changed it if I just close it up? Haven't done anything to it. It's still at about 1 atmosphere. But this is a device that is going to suck particles of gas out of the dome. What will happen to the pressure in the system? The pressure will decrease because gas pressure is the result of collisions of particles in the system on objects or on the walls. And I'm going to take some of those particles out. As I do so, I want you to watch what happens to the size of the balloon. Derek doesn't like loud noises, I won't burst it. Yeah, okay. What happened to the size of the balloon? Okay, the balloon got bigger. Boyle's law says that pressure varies inversely with volume. As we decrease the pressure, we increase the volume. I'd like you to think for a minute and to talk with the person sitting next to you about why. What's going on inside this system on a molecular level, atomic or molecular, that can account for the balloon growing in size?
The particles going out of it.
Yeah.
And then that makes more space for the balloon to expand.
Exactly, and because it's gas, each gas has a lower compressibility, lower or higher, then it allows the balloon's mass to increase, or the size of anything.
For sure, gas particles have balloons, so the other ones are taken out. That's pretty cool. I didn't get that.
Do we have a team that thinks they have a good answer? Jason?
The air pressure inside the balloon is trying to match the air pressure outside of the balloon. And so when it does that, it makes the balloon expand.
Okay, the air pressure inside the balloon is trying to match this. Okay, let's go a little bit farther with that and actually talk about the molecules themselves.
Yeah, when you're decreasing the pressure, the molecules are getting farther apart.
Mhm.
So that's the same thing happening inside the balloon. The molecules are getting farther apart.
That's
making
great.
it bigger.
That's really good. Did you guys get that? Visually, what that means is that this is our dome, and here's our balloon at the beginning. We have particles that are a specific distance from one another. They have a density that is the same as the density of particles in the dome. That's what causes the balloon to be a specific size. It has equalized, it's reached an equilibrium where the pressure on the inside of the wall of the balloon equals the pressure on the outside of the balloon. The spacing is the same. And this is, I gave you the hint when I said we're not really interested in the balloon, we're interested in making visible the air that's inside of it. So what we did was with the pump, is we took out some particles. And now the density of the gas is not equal inside and outside of the balloon, is it? So the balloon has to adjust its size so the particles inside it can spread out more, taking up more space, so that the density inside the balloon will equal the density outside the balloon. Pressure varies inversely with volume. As you decrease the pressure, the volume has to get bigger. We're going to stay with that a little bit longer with another demonstration. This is one of my favorites. It's called the Cartesian diver. It's probably one of my favorites because I played with one when I was a kid. How many of you had a Cartesian diver? You guys are old enough. How about a diving Tony? Tonight when you go home, ask your parents who had a diving Tony, because they used to put Tony the Tiger diving time in the Kellogg's cornflakes boxes. So instead of a dropper, you had a little tiger. Okay? What's the pressure inside the graduated cylinder right now? It's open, so it has to be the same as the room, and I'm about to close it up. What's the pressure like? It's the same. Okay, the pressure is room pressure. I haven't done anything to it. Now, can I borrow your hand? What am I doing to the pressure on your hand? I'm increasing the pressure by pushing on it. I'm going to do the same thing to this system, and the system is everything inside the graduated cylinder. I'm going to push on it. So what am I increasing? Woo, there's a lot of things going on here, isn't there? Lots and lots of things going on. And I'm going to ask you to do something a little unusual. Forget the diver right now and think about the graduated cylinder itself, okay? There's an air pocket between the rubber balloon and the top of the water. As I push in and increase the pressure, what is happening to the size of that air pocket?
Increase.
I'm pushing in, I'm indenting it. So yes, I am decreasing the size of that air pocket. I'm increasing the pressure and I'm decreasing the volume of the air pocket. Now, let's now finally look at the diagram that's in here. And what I want you to do is that have a look at the dropper, and I put it in a graduated cylinder so that you can kind of get a sense of the size of the air pocket that's in there. Now, you're going to have to keep focused on the gas, not the water. Okay? Watch what happens to the size of that air bubble as I push down.
It's smaller.
Smaller?
Yeah.
And watch what happens when I release it.
Since the water pressure is pushing the pressure inside the little.
Just the pressure inside the dropper has to equal the same as outside of it.
Kinda. We'll get to that. First of all, let's back up for a second. Pressure varies inversely with volume. There's a lot of things going on here. The first thing we want is not so much why does the diver go down, but why does the air bubble get smaller? Okay, pressure varies inversely with volume. If we increase the pressure, we expect the volume to decrease, and it does. Why? Very much the same reason that the balloon got bigger. We went in the other direction. Now we're increasing the pressure. Or, you know, we could turn it around. We could say, let's start our observation at the bottom. Here it's under high pressure and the bubble is small. As we decrease the pressure, the bubble gets bigger. And yes, it's very much the same. The particles are spreading out or coming closer together to match the pressure. As the pressure increases, the particles are going to come closer together so that they're under higher pressure. Why does the dropper go down?
It fills up with water.
Because it fills up with water?
A little bit.
So air decreases.
Oh,
The
you're
space
good.
between it decreases.
The air decreases. That's a wonderful answer. Is there actually less air
There's
in the
less
dropper?
space between the molecules.
There's less space? How many of you have ever floated on a pool and you've taken a deep breath in and you feel yourself go kind of high in the pool and then you let the air out and you feel yourselves kind of sink into the water? What is that we're adjusting? It starts with a B. We're adjusting our buoyancy by how much air we have in our lungs. The funny thing about it is it isn't really the mass of air that we have in our lungs at all, it's the volume of air. So even if we keep the same grams, the same mass of air, but we have smaller volume, buoyancy decreases. So when we put it under pressure and we cause the air pocket to have less volume, we decrease the buoyancy and the dropper goes down. There's less air in there, and less air means less buoyancy, and it's going to drop down. When the weight of the dropper is enough to cause it to sink, down it will go. You can play with these things for hours. I'm amazed nobody here has ever played with them. They're fun. Boyle's law, the inverse relationship between pressure and volume. Now, the proportions are really, really good. That first equation of pressure is inversely related to volume, and you're going to find me relating to it and talking about it a lot today. Notice that the 1 over the V, that's a fraction. That's how you indicate the inverse relationship. But if we try to plug numbers into that equation, we're going to get a little bit frustrated. It doesn't work real well. So let's take one more journey with a balloon and then try a math problem. Suppose you got a balloon in the mall, it's a helium balloon, and you go outside and you let it go. You know, your brother or sister let it go. Has that ever happened to you? Yeah. Where does it go?
Straight up.
Goes straight up. How high does it go?
Very high.
Till it pops. Why does it go?
Pressure.
The air
The pressure
pressure
is
is
like the
less
solid
pressure.
expanding as it goes up because it's trying
There's
to
less
equal that
pressure.
outside pressure.
Okay, very good. Why is there less pressure up there? Anybody?
Because higher.
The air particles are less dense.
Right, they're less dense. Gravity has pulled particles down to the bottom. They're thinner up there. We know that as you go up in altitude, there's less air pressure. As the pressure decreases, as the balloon goes up, the volume is going to increase, until it actually pops, because it goes past the expandable nature of the rubber. Let's actually put some numbers to this with a little bit of a Boyle's Law gas problem. Let's suppose you start out outside the mall with a 1 liter balloon. The equation is going to be pressure times volume equals pressure times volume. We can't use the proportion, we need to use it to pull together an algebraic equation. We're going to start with a balloon that has a volume equal to 1 liter. And as we step out of the mall, we're going to say that it's at normal sea level pressure, which it is here. So our pressure would be, let's use kilopascals, 101.3 kilopascals. Let's say we allow it to go all the way up there, really low pressure. Let's use a really absurdly low pressure. Let's say it gets all the way down really high to 300 kilopascals. Let's go ahead and calculate what volume our balloon would be. These are going to be just like the problems you're going to have for homework tonight. So let's try one out. You checked your answer with your partner? I haven't worked it yet. Before we call on you to give an answer, ask yourself, does your answer make sense? Our pressure has gone down. Boyle's Law tells us that what should happen to the volume if the pressure goes down?
Decrease.
It should do what?
Yeah, that's what I thought.
Increase. So without even picking up your calculator, you know the volume has to be greater than 1 liter.
Yeah, that doesn't
Right?
make sense.
So you did a 300 bigger than the 300.
Yeah,
Oh,
that's what I
I'm
thought too.
sorry, I meant 30 and I'm bad.
I was right.
Thank you. Let's do it with 30 because it's going up in the atmosphere. That doesn't make any sense.
That's confusing me.
It's like absurdly less.
See, with those numbers, that's what I was thinking. So I was right.
Okay, as usual,
Come in.
What'd you get?
3.388.
What'd you get?
3.388.
3.38? 3.4 liters? I figured we would want more than two significant figures. If it goes all the way up into a very low pressure setting, the balloon, do you think a balloon can expand to 3.4 liters without bursting? And of course, when they burst, they then fall into the ocean and they kill lots of sea turtles, so we try not to let really balloons go. Before we leave this, one more diver problem. Any of you interested in scuba diving or snorkeling? Okay. If you take scuba diving, are any certified divers here? Okay, so you know all about gas laws. I thought it was so cool when I took high school chemistry the first time because I knew the gas laws already. Suppose this represents not a graduated cylinder but the ocean, and you're on your checkout dive and you're breathing from the scuba tank down at 33 feet of water. So you're down there at 33 feet of water and you're breathing out of a scuba tank. What pressure are you at?
We're really high pressure.
Remember, 33 feet of water, or seawater, is roughly equal to 1 atmosphere.
So about 200.
No.
Under.
Well, in atmospheres.
Oh, yeah, 2.
You're at 2 atmospheres. You see a shark or something kind of exciting and nerve-wracking, and you forget what you're doing, and you kick off at the bottom of the ocean, and you go all the way up real fast while holding your breath. Actually, you're not deep enough to get the bends. That's something different. But you're going to be in danger of something called air embolism. Because your lungs are like thousands of tiny little balloons filled with air. And as you go up and you decrease the pressure, they increase the volume and they burst right through the sides of those alveoli. And the gas that's released into the bloodstream can lodge in your heart, causing a heart attack, or in your brain, causing a stroke. So when you take diving, they'll always tell you whenever you're at the bottom, you have to breathe out whatever you're going up to avoid that. The bends is related, but it's a little bit different. It has to do with solubility of gas. That nitrogen in particular is much more soluble under high pressure. And as you come up, it becomes less soluble and it comes out. But good. We're ready to look at our next law, which is Charles's law. It's not a pressure-volume relationship, it's a temperature and volume relationship. You'll notice that it doesn't look like boils. There's not a fraction. And in the word description, it says volume varies directly with Kelvin temperature. That's rather than inverse, it's direct. Remember now, inverse meant that when you increased one, you decreased the other. Direct means that they both increase together or they both decrease together. Let's look at a couple of demonstrations. For that, this is getting rather cold. I need very cold temperatures. So I'm making a really cold ice bath. I need a Bunsen burner and goggles. And Derek, I'll try not to make too many loud noises.
All right.
Okay.
Let's cut the one in first.
What I'm going to do is use my rigid container rather than a balloon to get a container that, this is 330 milliliters in size, and I'm going to fill it with really hot gas. To do that, I'm going to put a little bit of water, and I'm going to heat it up until the liquid becomes a gas and fills up the container. And our demo will actually begin, not now, but after I go from it being very hot gas to it being very cold gas. How will I know when the can is filled with hot gas?
Start seeing steam coming out the top.
When I start seeing steam coming up the top. And I'm seeing steam coming up the top. I know you can't, but I can.
I see.
1, 2, 3. Oh, see? I get.
We did this live in 6th grade.
I was surprised you hadn't seen the Cartesian diver. Temperature varies directly with volume. As you decrease the volume, you're going to decrease as you decrease the temperature, you're going to decrease the volume. Now, I have to admit there's a little bit of poetic license that's involved here. It's not just Charles's law that's in effect here, because I went from it being a hot gas to being, what happened when I put it at 0 degrees? Is it still a hot gas? It's not only a cold gas, it's a
Cold liquid.
It's a cold liquid. I forced a phase change as well, okay? If you look up, you know that hot water vapor would be 22.4 liters per mole, but if I cause it to become water, then it's only 18 milliliters per mole. So it's a lot smaller. So this is not just Charles's law, it's also a phase change. But nevertheless, it's going to work really well for a reminder during tests that as you decrease temperature, you decrease volume dramatically. And a lot of the volume decrease that we see here actually is still accounted for by Charles's law, and we'll work a little bit of a problem with that so that you can get the feel for it. The equation for Charles's law is a little bit different. It's, instead of PV equals PV, it's volume over temperature equals volume over temperature. Our volume started out at 350 milliliters. Now we have to be careful about the temperature. You'll notice on the board, volume varies directly with Kelvin temperature. Do you remember why we had to use Kelvin when we were doing kinetic energy? So that the graph would pass through something. Zero. Think about it, what size would this balloon be if it were at 0 Kelvin? The particles wouldn't be moving at all, so it wouldn't take up any space. You need it to have that direct proportion. It's got to be in Kelvin. You've got to be using a Kelvin scale for all gas cell. Okay? So if we started out in the flame, and let's nominally call it, I haven't actually taken the temperature of the flame, but let's say that we're at 400 degrees centigrade. And in Kelvin, what would that be? 673?
Yeah.
Okay, we're looking for V2. If we go down ice and water, what temperature are we at? 0 degrees. Okay. So our T2 equals 0 degrees centigrade, which is 273 Kelvin. Go ahead and calculate our V2 if all that was involved was just Charles's law. Before you want to check with the person sitting next to you, and you also want to ask yourself, does the answer make sense? According to Charles's law, if I decrease the temperature, what should happen to the volume? It should decrease, so it's got to be smaller than 350.
Yes.
What'd you get?
141 I should say 142.
Is he right? 142?
Yes.
Okay. Did our can get smaller than that?
Huh?
Yeah.
Yeah, it did. And again, that's how much of the volume decrease could be accounted for Charles's law. The rest of it was phase change. Okay, we actually did have the water going through phase change, taking up a lot less space. And I don't know what the volume is inside of this fresh can, but it's a lot less than 142 milliliters. Okay. Next, Gay-Lussac's. The pressure of a gas is directly proportional to the Kelvin temperature. Is Gay-Lussac's law more similar to Boyle's or to Charles? You'll notice that once again it's got the word direct or directly, and when you look at the proportion statements, there's no fraction. It's very similar to Charles's. When temperature increases, pressure increases. They vary together. Increase one, you increase the other. The best example that I can think of this is aerosol cans. And you have a lot of, I don't know if you have a lot of aerosol cans at home or not. What comes in an aerosol can? I heard a shaving cream. Something else? Spray paint? Spray?
Some
Deodorant?
deodorant.
Yeah.
Some of them. Okay. Some deodorants are aerosol cans. They all have a warning on them, don't they?
Don't inhale.
Aside from not inhaling, what don't they want you to do with an aerosol can?
Don't heat it up.
They don't want you to ignite it, they don't want you to incinerate it, they don't want you to store it near a fireplace.
They don't want you to like break it open because it's under pressure.
Yeah.
Okay? But let's first look at the temperature, because that's what Gay-Lussac's law is looking at. Pressure varies directly with temperature. If we throw it into a fire, we're going to greatly increase the temperature, we're going to greatly increase the pressure, until, of course, it ruptures, because there's too much pressure on the sunlight. And the equation for Gay-Lussac problems is very, very similar to Charles, because they're both direct relationships rather than inverse. And what we have is pressure over temperature equals pressure over temperature. Are you beginning to feel like there's an awful lot of equations you're going to have to memorize?
Like 3.
There's only 3, actually.
Two of them are the same.
Actually, all 3 of them are the same. Because, watch, what happens if I put a volume in here?
It's Charles. Alright.
It becomes.
If you get rid of the T's, it's
Boyle's law.
Very good. If you get rid of the T's, it's Boyle's law. If you get rid of the P's, it's Gay-Lussac's. If you get rid of the P's, it's Charles. This is called the combined gas law, and I encourage students when they're doing problems to kind of use that and take away what you're not working with. So I'll go ahead and I'll remove the volume since we're about to look at a Gay-Lussac, a pressure-temperature relationship. But there really aren't 3 equations. There's one, and then you only use what you need to use. Let's suppose our aerosol can is well, a normal aerosol can. Would it have a pressure above or lower than room pressure?
above.
Has to be above. Let's call it a pressure of 200 kilopascals. And let's say it's at room temperature equal to 23 degrees centigrade. Now in Kelvin, that would be
300.
296.
96 Kelvin. Let's suppose we threw it into a fire where the temperature was 600 centigrade.
873 Kelvin.
Derek, what was that?
873 Kelvin.
Go ahead and find what pressure you'd be dealing with.
Mine said T2 and T3.
I got it.
Oh, this is T2 in Kelvin.
Yeah.
Hang on there. There you go. Once again, use your common sense and ask, and this is something students really forget to do. I'm increasing the temperature. What should happen to pressure?
Increase.
It should increase. So before you even pick up a calculator, you know that your answer has to be greater than 200 kilopascals, or you did something wrong. We're going to finish with grain teaser. What'd you get?
590.
590?
Yep. Yeah, Pascal.
I'm seeing some questions. Did y'all convert to Kelvin?
Yes.
Oh, okay. Okay. Brain teaser, which gas law? Or making it simpler, how did I do this? I have a balloon and a flask here. Any volunteers that want to try to do it?
It's Boyle's
What's in
law.
there?
You cool it down.
Oh,
Okay.
yeah.
Gotta be Boyle's?
Frozen.
No, you
Would that be
melted it.
Boyle's then, like frozen?
You pulled it down to
That'd be
decrease
Charles.
the pressure.
If I did,
Yeah, that's
You pulled it down to decrease the pressure, which decreased the volume.
but I thought this balloon's big.
You have to decrease the pressure
You have
inside
to
the flask.
decrease the pressure inside the flask.
It's inside
Or
the
you
balloon.
could decrease the temperature.
If I,
Or you could increase the pressure in the balloon.
That's right.
I'll give you a hint, I did it without any fancy machines or anything. I didn't have a pump or anything.
We went to that whole one.
Yeah, water.
Hmm? It is Charles. Yes.
If you want bigger volume, you can have higher.
If I cooled this down, if I got this really, really cold, what would happen to the balloon? I'll give you a hint, you're looking at the wrong airspace. The balloon is open to the room,
Yeah, that's
but
what
the
I was talking
flask
about.
is not. It's the air pocket between the balloon and the glass. Which one has a bigger space? This one. So I did something to decrease that space, didn't I?
You cooled
Yes,
it.
you can.
Cooled it all the way down. What I actually did is I heated it all the way up first and filled it with steam just like I did with the can. And then I put the balloon in and cooled it all the way down. You gonna do it again? Let's see it done. It actually takes a while because to get it to work, you need to let it cool slowly. So I'll let this go. Okay. And I'll do this while you're what I'm gonna do is I'm gonna let it sit and vaporize, and I'll go ahead and put one in for you to look at. But it's probably gonna take a good 10 minutes for this to fill up and be there. And I'd like you to have a chance to do some of this work. You don't have to do it in the order that it's on the board. It actually would be better for you to try the math problems while I'm here to help you, rather than the essay type ones. The question was, when is this due? And my answer was that you should try to do at least the math problems before tomorrow, so you'll know what you need help with. But if you don't get all of them done, it's okay. I'm going to be pushing this week to do this chapter before Friday. I'm trying to keep my classes all together, and Monday is FCAT. I don't want to let it sit until after FCAT. And we've done more than half the chapter already. Isn't that horrifying? Okay, it's a little chapter. We're done here. One person out of every two, please go get a book so you can get started. What do you think? How did it come out for you?
Pretty good.
Pretty
Thing
good?
was loose and it felt very.
Ah, that's. Yes. To actually put the procedure into your lab book that you will actually follow. Keep in mind that the aim of the lab is not the aim of this sheet. The aim of this sheet is to help you design an experimental procedure. What's the aim of the lab?
To discover to find the change in combustion reaction for people.
Right, to write a thermochemical equation for the combustion of paraffin wax, including the energy statement, the enthalpy statement. So that's your actual aim. You have the title, and you're going to work together in your groups of 2 or 4 to put together a good procedure that when you come in tomorrow, you can just do. Tomorrow, I'm not going to say boo. I'm going to say, go to the hello, I'll take roll, and say okay to the benches. Okay. Yes, thank you.
We're gonna move forward.
Oh, let me just down here.
Our aim is to find graduate for that.
Did you get it?
Yeah.
Get rid of the
They left me. And they're excluding,
I know, so the aim is not.
they use.
I know the aim of the law, that's wrong. To find, to find the thermodynamic equation of the combustion of candle wax, including the enthalpy, heat of enthalpy.
I'd say that somebody accidentally that's right though. I don't think they really stole it.
Well, I didn't figure it out.
You know, you said something and magically it's large. I won't count it. I won't count it, I haven't graded it.
I'm on TV.
Okay.
The air visible to us. The balloon is not insured. Inside the balloon is trying to match its pressure. We expect the volume to decrease, and it does. Why? Boils. There's not a fraction. And nominally call it, I haven't actually taken the temperature of the flame, but let's say, are you beginning to feel like there's an awful lot of equations? Before you even pick up a calculator, you know that your answer has to be